Hello, this is Nick of Time. Welcome to the sixth talk of this series. Last time we talked about relative velocity, relative momentum, relative kinetic energy. All of those constructs have time as part of their definition. Today we're going to talk more directly about time in terms of simultaneity and synchronization of clocks. Okay, if you're using special relativity, then all your clocks need to be synchronized by the Einstein clock synchronization procedure. In fact, if you've used that procedure and you're in one inertial frame, and then you go to another inertial frame, either the clocks in that new inertial frame have to already have been synchronized by the Einstein clock synchronization procedure, or if you're carrying all your clocks with you, you have to resynchronize them in terms of that Einstein procedure. Okay, the Einstein synchronization procedure assumes that the speed of light is the same in all directions for all inertial frames. We're going to see that basically what's assumed by the synchronization procedure guarantees that people will observe the speed of light to be the same in all directions, in all inertial frames. But if you think about that, that really can't be true, as Dingle and others have pointed out. And a little thought should point that out. Okay, if one uses the Einsteinian synchronization procedure to synchronize clocks, then if you use those clocks to measure the speed of light, you'll find that the speed of light is the same in all directions. Let's take a look at a diagram to better understand that. Here we're going to try and synchronize clock B with clock A. We send out a light signal from clock A to clock B, and it's reflected back to clock A, and A records the total time of transit out to B and back to A as 2 seconds. Well, since the Einsteinian synchronization procedure says that the speed of light is the same in all directions in all inertial frames, it's calculated that light took 1 second to go from A to B and 1 second to go from B to A. The B clock will be set according to that assumption. However, let's say that the ray of light from A to B really took just 0.9 seconds. And the return trip from B to A took 1.1 seconds. However, remember, the B clock was set by the erroneous Einsteinian synchronization assumption. So the B clock is set according to that assumption. But that assumption means that clock B will be biased by 1/10 of a second in the positive direction with respect to A. And if you use that same procedure with clocks on the same line between A and B, the further you go out to the right, the larger that bias will be. Similarly, if you go in the opposite direction from B to A, then you'll have a negative bias, and the further you go out to the left, the larger that negative bias will be. And the bias will be set so that if you use those clocks to measure the speed of light, you're guaranteed to measure the speed of light as being the same in all directions. Okay, back to the previous slide. Look at the third point. So what has happened? Well, Einstein has redefined the concept of time in terms of the speed of light. without much comment by Einstein himself or the physics community. And it really is a change in the wrong direction. In addition, that procedure has implemented an erroneous concept of simultaneity. Namely, relative simultaneity. I need to emphasize one more very important point about Einsteinian synchronization. For Einsteinian synchronization to correctly synchronize clocks so as to, among other things, correctly establish simultaneity, the assumption that it's based on must be consistent with the physical world. Just being consistent with how the world is observed would not be good enough. Unfortunately, it cannot be physically true that the speed of light is physically the same in all inertial frames in all directions. But Einsteinian synchronization is needed by special relativity to have all inertial frames simulate the one preferred frame, which is the one frame where the speed of light is physically the same in all directions. Okay, that's the main topic of this talk, Einsteinian synchronization. But there's a related topic. It's by no means anywhere near as important, but it makes sense to cover it now. We're going to look at the standards for time and space units. First, the second is defined as the duration of that large number of periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. Okay, that's an operational definition of a second. A very good definition. It's a good physics definition of a second. I have no problem whatsoever with that definition. But now let's look at the definition of a meter. And I guess that's the British or the European spelling. The meter is defined as the length of the path traveled by light in a vacuum in 1 divided by 299,792,458 seconds. But that is defining the meter, or space interval, in terms of the speed of light. That makes it so that if you're measuring the speed of light and you're using and have implemented that definition of the meter, you will always measure the speed of light in a vacuum as 299,792,458 meters per second. So by definition of how they define the space units, you're going to measure the speed of light, always measure the speed of light as c, the constant. Well, again, thank you for joining us for this sixth talk. I hope you join us again as we continue to look at special relativity as a frame-centric theory and see the limitations of that type of theory. So I hope you join us next time. We'll be talking about the twin paradox and proper time.